Hello everyone. Today we will discuss about buck DCDC converter with analog voltage mode control and the type 3 compensator. So, voltage mode control. Well, it refers to the way the duty cycle is created or it is derived. Basically, we have a comparator which has at one of its inputs the control voltage, which is output of a error amplifier, and on the other input we have a voltage ramp which is generated externally to the circuit and has nothing to do with the specific operating point of the converter. So you can actually see it here from the picture. As long as the ramp is below the control voltage, the comparator output is, let's say, logic 1. That means the switch is closed, and then we take energy from the input voltage source. As long as the ramp becomes greater than the control voltage, then the output of the comparator switches to 0, and then the MOSFET is turned off or the switch is open. So simply by varying this control voltage, we are actually controlling the duty cycle of the control signal for the MOSFET. Okay, so that's voltage mode control. You can identify we have only one loop, so we are sensing the output voltage normally by a resistor divider, and we have this reference level, and what this error amplifier is trying to do is to bring the non-inverting input to the inverting input to the non-inverting input reference voltage. Okay, then we already seen in a previous video how to extract the power stage transfer function, and what we can actually see here is that we have a complex pair of poles at the resonant frequency of the buck inductor and the output capacitance. And we also recall that in the end, in open loop, we want to have a system that has a minus 20 dB per decade slope. So what we need to do is for this plant or for this power stage, we need to attach the compensator, the frequency compensator, employing an error amplifier, and we expect that this will have a pole in the origin, so that we will have that slope of minus 20 dB per decade. Then at this resonance point, we saw that we have abrupt change of nearly 180 degrees in phase. So basically what we want to do is to compensate the effect of those two poles, and therefore we will need two zeros. And later on we would need at least one more pole to compensate the effect of whatever zero is presented in the power stage transfer function due to the parasitic series resistance of the output capacitance. So I just said we would probably need at least two poles and two zeros. So actually what we can identify in the types of compensators in the analogic design is what is called a type 3. So a type 3 compensator, you can see it like this. It is built around a voltage error amplifier. There are also possibilities to do this type 3 compensator with a transconductance amplifier. So as I said, we had this resistor divider, which is built with R1 and R2, and then a compensation network. Of course, R1 it will be part of the equations. R2 not, because in actually this non-inverting input, as I said, will equal this reference, so voltage over this will be virtually zero. That means it will not contribute. Okay, so this type 3 compensator has 3 poles and 2 zeros, as you can see here in the picture. So we have the pole, the origin. We have two zeros then, and then 2 poles, and this is the transfer function describing this circuit. Of course, for the zeros, we can do some identifications. Yeah. Okay, so now we know that, for instance, omega p0 equals 2 times pi times fp0, which is the frequency at which the pole in the origin is placed. So rather than doing a manual placement of the poles and zeros, we will use the k-factor method. The k-factor method this concept was developed by Dean Venable in the 80s, and it is very well and nice presented by Christophe Bassot in his book Switch Mode Power Supplies, Spy Simulations and Practical Designs. Actually, the short explanation here is extracted from Bassot's book. So actually, this k-factor, it will be a number that will be calculated based on some inputs from the power stage Bode plot. And then what will actually do, it will automatically place the zero and the pole, or the for the type 3, the 2 zeros and the 2 poles at equal distance in regards to the selected cutoff frequency, so that it will be like as it's written here, the geometric mean between these respective locations, and in the end here at FC we will have the highest phase boost. Okay, so now if we want to have this design for the type 3 compensator with the k-factor method or concept, as I said, first we need some information from the Bode plot of the power stage. So we will of course we will select cutoff frequency. We will look at the gain and phase on the power stage Bode plot at the selected cutoff frequency, and then we need to impose a certain phase margin we want to have, and we need to calculate two values like the needed phase boost and the required gain at the cutoff frequency, and then by using those values we can actually calculate the values for the components. So here actually the position of the pole at the origin, because it is important, this position of the pole at the origin will make the gain curve to hit 0 dB at the selected crossover frequency. So if in a manual placement of poles and zeros, you need to calculate the frequency where the pole at the origin needs to be placed. Here, this is not visible. Actually, it is embedded in all those equations. Yeah. Okay, but let's see a step-by-step compensator design. So first step would be clear that we need to choose a cutoff frequency for our analog buck converter. So we know we are operating with 100 kilohertz, and we know the rule of thumb for the analog designs would be that the maximum cutoff frequency should be like switching frequency over 10, so 1 decade below. Therefore, we are choosing this 10 kilohertz as the cutoff frequency. Second step is from plant transfer function. We just put a cursor, we enter here 10 kilohertz, and then we need to extract the gain value and the phase value for 10 kilohertz. So here it's almost 2.4 dBs, and here we have minus 174 degrees. So those are the two parameters extracted from the power stage body plot. Third step, then we need to define a reference voltage here, and for convenience I selected to be 2.5 volt. We know that we want to have 5 volt at the output, and then I also impose the value for the upper resistor in the resistor divider as being 10 kilo ohm. That means also R2 will be the same value, yeah, because having here 2.5 volt, I just need a division by 2 from the 5 volt to get the 2.5 at this midpoint. And of course, we need to impose or to select a value for the phase margin we want to have at this cutoff frequency. Okay. Step number 4, we need to calculate the intermediate values like the required phase boost, the gain we need at the cutoff frequency, and especially the K factor. After we do this, then the last step, the step number 5, would be to calculate the values of the components. And here you can see for C2 I ended up with 2.1 nanofarads. Then we will use in our simulation a 2.2 since this is a standard value. C1 81.6, 82 is a standard value. R3 is 1.2K, it's already a standard value. R4 257 ohms, so 255 is a standard. And for C3 we are very close to 10 nano, therefore we will use a 10 nano 10 nano as a standard value. Okay, now it's time to move to the simulation. So actually what I did around the power stage, I AC simulation employing the 3-terminal PWM model, I build up the type 3 compensator, and I just used a voltage controlled voltage source for the operational amplifier. That's like having an ideal with infinite bandwidth and whatsoever for the operational amplifier. But of course you can modify this if you want to have a more closer to reality op amp. However, for the frequencies of interest, this is absolutely fine. Okay, so we have the values we just discussed. We have this low pass filter built with this L2 and C5. This is actually low pass filter with a very low cutoff frequency, so 1 kilohenry with 1 kilofarad, and this is actually breaking the loop, yeah, to say like this. So we will be able to plot the open loop response of the power stage plus the regulating by simply plotting this VC, I mean control voltage. Actually in DC operating point or in steady state, the inductor and is a short circuit, the capacitor is an open circuit, and then we still have or the circuit can still have the possibility to get or to calculate its DC operating point, but then in AC the loop is actually open. Yeah. Okay. So what we can see here is I plotted this control voltage, and I placing the cursor and select it here with the double click, enters 0. It goes to the minimum value close to 0 it can find. In this case is minus 900 micro dBs. And at this point you can see we have a 9.9 kilohertz, and we have so this would be the cutoff frequency for 0 dB, and then at this point we have like 59.7 degrees phase margin. So it's exactly what we expect it to be. Okay, let's now try to go here. Yeah, exactly. So this is what I was saying. I can even run it again, but um, yeah, gives the same result. Okay, good. Then it's time to move to transient simulation. And in transient simulation, we can extract the open loop transfer function of our buck converter by using the .bode statement. And this time I used this generic rail-to-rail operational amplifier. I also tried in the AC simulation, but it doesn't work. I don't know for which reason. Yeah, so but here with this model, and I can switch back to the but here with this model you see there are some parameters. You can define the open loop gain, the gain bandwidth, the slew rate. So yeah, this you can have a closer to a real op amp model here by simply implementing some values here. Okay, so let's see. This one takes a bit longer time. Okay. I don't know, I can't see it. No. Yeah, okay. This is a bit embarrassing. But you have to trust me. Oh, nothing seems to work. However, I was able to spot it for a second, or less than a second. Okay. So the simulation takes a bit longer, like 17 seconds, but in the end we get this result, which is again as we expected, very close to our values. So for like 0 dB here we have like 9.77 kilohertz and 60 degrees phase margin. So that's it for today. Thank you for watching. Goodbye.